Hello everyone, my name is Rosa. I am a master student and my advisor is Professor Sandra Avila. I am going to present our work exploring explainability deep learning methods for skin lesion analysis. I am going to start with the motivation for this work. Cancer is a set of diseases characterized by the uncontrollable growth of cells, which can invade surrounding tissues, causing people's death. Last year, in 2020, we had over 19 million new cases worldwide and nearly 10 million people died from cancer. For the skin, we have several skin cancer types, being melanoma the most aggressive. So much that it is compared to other cancer as if it were a single organ. For melanoma, the numbers of new cases were more than 300,000 people worldwide and about 57,000 deaths. So, how can we help save more lives? According to the World Health Organization, cancer can be cured if detected early enough. Diagnosis of skin cancers starts with a physical exam, where the doctor asks some questions such as the date the lesion appeared, if it is painful, or if the lesion color or size has changed over time. Then, if the doctor thinks it might be cancer, proceeds with the next step, where the dermatologist takes an image with a device called dermatoscope, which is a device that eliminates the influence of light on the lesions, as we can see in this image. We have here in the left clinical images and on the right dermoscopic images. The dermatologist assesses the presence of attributes such as point, stretch marks, streaks, color, shape, among others. If the dermatologist thinks it may be cancer, a biopsy is done. Therefore, we as computer scientists can help dermatologists by developing tools that automatically give a diagnosis. With this aim, the international collaboration for skin imaging has been organizing competitions since 2016 with various databases and tasks, such as the classification of type lesions, malignant or benign lesions, using or not metadata. Last year's winner used an ensemble of 18 convolutional neural networks, getting a score of nearly 95%. However, an important step towards not putting people's lives at risk is to understand what these models are relying on to make these predictions. So, having a high prediction accuracy is not sufficient for real-world applications. Currently, we have critical domains such as medicine, healthcare, criminal justice, financial lending, that base their decision on the output of DNA. But how to entrust humans' life to a black box system? So, we need to understand why neural networks predict what they predict. This area is called explainable AI, and it is necessary to increase the confidence on DL models, to know whether a model is robust to adversarial attacks, to facilitate the detection of bias and debugging, to know if a model is ready for deployment, and to accomplish with legal regulations. We have several ways of explanations for neural networks. The most popular one is feature-based explanations that will assess the importance of the contribution of features in the prediction, such as the saliency maps that highlight the most important pixels, We also have surrogate explanations that make an approximate prediction of a black box network using an interpretable network such as linear regression or decision tree. And another way of explaining networks is using explanations based on high-level concepts. For example, a phase rabbit and a stripe concept. Now let's see what is the problem when these methods are applied in the medical field, especially in the case of skin lesion. Current explainability methods based on saliency maps have not been getting good results, as we can see in the image. In the second column, we have GradCAM results, and on the third column, occlusion results. Likewise, line method on the BGG16 network, the 2016 winner, got results where that explanation showed that the network was using features that go beyond the injury part. Thus, adapting explainability methods that were originally developed for tasks that use a database such as ImageNet for the medical imaging environment is quite challenging due to the homogeneity in the data. The target model used in this study is a skin lesion classifier using inception before architecture pretrained on ImageNet and fine-tuned with ISIC 2018 images. The model obtained more than 95% area under the log curve, and we choose this model because it has demonstrated previously to have a good performance in skin lesion analysis. The methods used to explain this model are ScoreCAM and automatic concept-based explanations, more known as ACE. ScoreCAM is a method based on class activation mapping. Given an input image and a trained model, the method will extract the activation in a specific layer of the network and apply them to the input image as masks, creating new images. Then these new images are passed through the convolutional neural networks, and to get the score, a linear combination of the predictions and the activation maps is performed. Then we get a saliency map where the most important pixels are highlighted. ScoreCAM is a local method, which means it produces a different explanation for each prediction. Here we have the input image, the heat map, and a superimposed image. In order to evaluate these explanations, we divide them according to the correctness of the prediction. First, true positive, where the model correctly classified the melanoma class, and true negative, where the classifier correctly predicts benign lesions. In the first column, we see ScoreCAM highlights the skin lesion, and in the second column, ScoreCAM finds spurious correlations in the model. For example, visible artifacts introduced during the image acquisition process, such as skin hair, row marks, patches, gel bubbles, and pen marks. Likewise, for the images where the model got a wrong prediction, the explanations show how for some cases the model bases its decisions on surrounding parts of the skin lesion and other artifacts such as ruler. However, these explanations are insufficient because it is only saying the classifier predicts the melanoma class because there is a skin lesion, but it does not provide any further information to support the prediction. Another method we used was automatic concept-based explanations with clustering, ACE, a global method that explains a model reasoning according to a class label, and the explanation is valid for all the data in the class. How does it work? Given a set of images from the same class, ACE applies a segmentation to all the images and groups the activations of the superpixels to form concepts using k-means clustering, and once it has the concepts, uses T-cap for the concept's importance. And T-cap works like this. Giving examples for each concept and the model, T-cap finds a representative vector for the concept using the activation of the examples. And to quantify the importance of the concept for the class, it calculates the directional derivative of the prediction with respect to the concept vector. So, here we have 4 randomly selected examples of the top 4 important concepts for the class melanoma. Here we have the segments that are the concept examples, the original image it was segmented from, and also we have the image highlighting their dermoscopic attributes, where pink represents globules, blue media-like cells, sky blue negative network, green represents pigmented network, and red streaks. Unlike a score count, where we had an area highlighted, with ACE we get the segments that are most important in the image, so we can compare them with the dermoscopic attributes. However, as we can see in the images, these 2 first concepts represent skin segments. The next 2 most important concepts shows skin segments again, so the top 4 extracted concepts with ACE are not even closer to the dermoscopic attributes. This could indicate the model has learned new things or things that are not important for predicting melanoma, but certainly the extracted concepts are not related to relevant clinical information. So, our conclusions and future work are: silencing methods are difficult to evaluate and do not provide a sufficient explanation. And we are going to explore more methods based on concepts, such as SIMI, a concept-based model extraction that is going to use textual attributes, and invertible C, invertible concept-based explanation. So, feel free to contact me if you have any question or comment. Thank you very much for your attention.